Welcome back to Casiorn Thinks. So, have you been looking at the news lately, seeing AI write code, pass the bar exam, and generate videos, and found yourself asking, what happened? You are definitely not alone. For decades, AI language models were, frankly, incredibly slow and had terrible memories. But then, in 2017, a single research paper changed the world overnight by introducing something called the transformer. Today, we are opening up the hood of modern AI to look at the actual gears, no marketing paint, no mysticism. We're going to explain how AI learned to pay attention, why size actually does matter, and how a simple trick turned AI from a slow reader into a high-speed relationship mapper. Let's get started.
To really get why the transformer was such a revolution, we first have to appreciate the problem it was built to solve. For a long time, if you gave an AI a sentence, it couldn't just, read it. It had to process it one piece at a time. So the earliest models, which we'll talk more about in a second, would look at the very first word, try to process it, and then do their best to hold it in memory. Then they'd move on to the next word, try to figure out what it means in the context of the first one, and just keep going like that. This one-at-a-time approach, as you can imagine, made them painfully slow. But what's worse, it was kind of like trying to read a whole novel through a tiny little mailing tube. By the time the model finally got to the end of a long sentence or a paragraph, it had pretty much forgotten what happened at the beginning. The context was just gone.
So yeah, this brings us to what I like to call the dark ages of AI language models. This whole one word at a time problem was the fundamental bottleneck that held the entire field back for years.
Okay, so the official name for these older models was recurrent neural networks, or RNNs for short. And their defining feature was exactly this, step-by-step processing. The output from one step would become the input for the next, which created this sort of internal memory loop.
But here's the thing, this sequential approach had one massive, crippling flaw. The technical term for it is the vanishing gradient problem. Now, that's just a fancy way of saying that as information passed from one step to the next, it would get weaker and weaker, kind of like a radio signal degrading over a long distance. Important context from the beginning of a sentence would literally just fade away by the end. So you can see the problem, right? This created a really clear set of limitations for AI. We can lay them out right here on the left. The models were slow because you couldn't do things in parallel, and they had just awful long-term memory. This was the wall that everyone in the field was running into.
So, how did the field finally break through that wall? Well, the solution wasn't about giving the AI a better memory. It was about giving it a completely new way of reading. The whole field was completely stuck on this problem of sequential processing and this terrible memory issue. So what was the solution that just blew the doors wide open? It came from a single research paper from a team over at Google. And with a deceptively simple title, Attention is All You Need, it introduced a revolutionary new architecture that basically threw the old rulebook out the window, the transformer. Instead of that tedious word-by-word reading, the transformer uses this brilliant mechanism called self-attention. It lets the model look at the entire sentence, the whole document even, as one massive block. And for every single word, it calculates how relevant every other word is to it, creating this incredibly complex map of relationships all at once. Okay, this is where it gets super cool. We can actually understand this with a great analogy from IBM's research. Think of it like a tiny little search engine that runs for every single word. The model creates three things: a query, a key, and a value. The query is basically the word asking, hey, who's related to me? The keys are like the titles on all the other words saying, this is what I'm about. And when a query finds a good match with a key, the model then pulls the value, the actual juicy information from that word. And it does this for every single word all at the same time. And that is the solution. It's just brilliant. So let's fill in that comparison chart from before. All of a sudden, processing is parallel, which makes it absolutely perfect for modern GPUs. The speed goes from slow to massively fast. And the memory problem? Well, the model now has a direct connection between every word and every other word. It doesn't forget. I mean, it is a total night and day difference. But here's the crazy part. This ability to process everything in parallel wasn't just a speed boost. It unlocked a secret weapon, a whole new dimension of scale that pretty much nobody saw coming. Researchers, especially over at OpenAI, discovered what you can basically call a cheat code for making AI smarter. It's now known as scaling laws. This paper from Kaplan and his colleagues in 2020 showed that if you just kept making the model bigger, fed it more data, and threw more computers at it, its performance would get better in this surprisingly predictable way. Then, in 2022, the Chinchilla paper from DeepMind refined this idea. It showed that you get the absolute best bang for your buck when you scale up the model's size, that's the number of parameters, and the amount of training data in proportion with each other. You can't just have a giant model and a tiny dataset. You gotta grow both of them together. And this realization led to an absolute explosion in model size. I mean, the ability to train in parallel meant we could build models on a scale that was previously just unimaginable. This all culminated in these behemoths like GPT-3 with an astonishing 175 billion parameters. And a model this big did something that nobody really expected. It developed this surprising, almost magical new capability called in-context learning. This meant you could give GPT-3 a task it was never, ever explicitly trained on, like, say, translating English to German, just by showing it a few examples in the prompt. It would just figure out the pattern. This was a true game changer. But there was a catch. Of course there was a catch. A very expensive catch. This superpower of looking at every word all at once creates a massive computational problem that threatened to stop all of this progress right in its tracks.
The problem is known as quadratic complexity, or O of n squared. In simple terms, this means the amount of computation and memory you need for self-attention grows exponentially with the length of the text. So if you double the length of your document, you don't just double the work, you roughly quadruple it. This creates a very real memory wall. To get around this wall, researchers developed some incredibly clever new techniques. One of the most important is called FlashAttention, from a 2022 Stanford paper. Now, it doesn't change the math of attention, but it acts like a brilliant traffic controller for the data on the computer chip. It reorganizes how information moves around to avoid these traffic jams in the slower parts of the chip's memory. It's really a pure efficiency hack that drastically speeds things up and makes it possible to process much, much longer documents.
So when you peel back all the layers, the transformer didn't win because it was some kind of magic. It won because it was an incredibly scalable relationship mapping machine. Its parallel design was the key that unlocked the incredible power of those scaling laws. And this begs the final really provocative question that the whole field is wrestling with right now. Is this incredible architecture the final word, or is it just the first step on the road to something even more profound? If you found this explainer helpful and it cleared some things up for you, be sure to like and subscribe for more deep dives into these complex topics. Join us next time as we look at the All-IMA project and how you can run these powerful AI models right on your own computer. Thanks for watching.